tomorrow will be the last day.
Sure, sir.
Video on.
Good evening, Professor sir.
Good evening.
Sir, kindly switch on your camera, sir, if possible.
Yeah, I do not know whether they have camera here or not, but I will. No, it doesn't seem like. This is a new room, and
Oh,
yeah, I just turned on, but it just doesn't come. So how is the preparation going on?
Sir, we have started, sir, already. The people have started.
Okay.
Only problems we are trying to solve from book. Already you referred the book.
Yes. Yes.
So team is.
I think if you go through the notes and the slides and you start solving problems, you will be fine.
Sure, sir.
And you all have seen our midterm papers. Have they shared with you the marks and papers?
Marks I received it, sir, but papers they are not shared. It's not a problem.
Okay. So I think most of you have arrived, so we can get started.
Yes, sir. Oh.
Recording in progress.
So today I plan to solve some questions on thermal conductivity measurement. And tomorrow I would solve some questions related to bulk mean temperature. And we had also missed to solve some questions on radiation heat transfer. That is the high temperature measurement. So that I had missed out. That also I would try to solve 1 or 2 questions tomorrow. So today we talk about questions related to different methods that we came across while we studied thermal conductivity measurement. So the first question is on a guarded hot plate apparatus. So a guarded hot plate apparatus is used to measure thermal conductivity of an insulating material. The specimen thickness is given 25 plus minus 0.5 millimeter. The heat flux is measured as 80 watt per meter square, and that is having an uncertainty of 1%. The temperature drop across the specimen under steady state is 5 plus minus 0.2 degrees centigrade. And you are asked to determine the thermal conductivity of the sample along with its uncertainty. So this guarded plate apparatus, I would just briefly describe. So it is basically having a heater at the middle. Okay. And the sample is here. And so basically the samples are placed on both sides. So these are basically samples. This is the heater. So, and then you have some kind of cooling arrangement. where flow goes in and flow comes out, and similarly you have on the top side also where fluid goes in and comes out. This is the heater. So as we discussed, so these areas are insulated. So this is insulated. This is also insulated. So the purpose of these insulators at the ends is that strictly the temperature, the heat flow direction is going to be one-dimensional. From the heater, temperature is going to go through the sample purely one-dimensional. Okay, so it is 1D heat conduction. So as you know, in case of one-dimensional heat conduction, you have this Fourier law of heat conduction, which says that the heat flux through a material is minus thermal conductivity times the temperature gradient, dt over dx, right? This is the rate of heat transfer per unit area. Typically, you will have a unit of watt per meter square. This is the thermal conductivity, right? This is the temperature gradient, okay? So if you want to measure thermal conductivity, you have to measure the heat flux and divide by the temperature gradient dt over dx with a negative sign. Now, in this case, your thickness of the specimen is taken as delta, right? So the specimen thickness is delta. And if you know the temperature difference delta T across the specimen, you can write this as the heat transfer that goes through the specimen divided by delta T divided by delta. Okay. So if I take a mod of that, I can observe the negative sign. Typically, dt by dx is negative because temperature always reduces in the direction of heat flow. That is what the sign basically makes the quantity positive. So when you evaluate the temperature gradient, if you take the modulus of that, you can observe the negative sign in there. So basically your K is going to be Q into delta divided by delta T. Okay. So this is the formula. Okay. Now in this case, you look at the question. You have a guarded hot place apparatus. This is used to measure thermal conductivity of an insulating material. Specimen thickness, the insulating material thickness is 25 plus minus 0.5 mm. First, you just take the nominal value, delta is 25 mm. That is 0.025 meter. Then the heat flux, that is Q dot, is 80 watt per meter square. Right? The temperature drop across the specimen, delta T, is taken as nominal value is 5 degrees centigrade. Okay. So all these three quantities you actually know. So you can find out thermal conductivity K to be Q dot, that is 80, divided by delta T is 5, right? And delta is 0.025. So if you calculate this correctly, you are going to get this as 0.4 watt per meter degree C. Okay, so this is the unit of thermal conductivity. Now, that is the first part of the question, that determine the thermal conductivity of the sample along a sample. The second part says its uncertainty. Okay, now the delta has an uncertainty, the heat flux has an uncertainty, and the temperature drop also has an uncertainty. All three have uncertainties. So we first note down the uncertainties. So U of delta is plus minus 0.5 mm, that is plus minus 0.0005 meter. Second is the heat flux is 1%. Okay, that is the uncertainty. So the uncertainty in the heat flux is plus minus 1% of 80, right? 1/100 into 80 watt per meter square. That is going to give you plus minus 0.8 watt per meter square. Next is the uncertainty in the delta T. So U delta T is plus minus 0.2 degree C. So you have three different uncertainties, and then you can also find the gradients. So basically your K is this. So you can find out dou K divided by dou delta, that is Q dot over delta T. Similarly, dou K over dou Q is delta over delta T. Similarly, dou K over dou delta T is going to be minus Q dot delta delta T square, right? So you have all these, so you can actually find out uncertainty in K is Q dot over delta T into U delta square plus delta over delta T into UQ square plus minus Q delta T square into U delta T square root. So you can substitute for everything. So your Q dot is 80, delta T is 5, and U delta is 0.0005 square. Delta is delta T is 5 into UQ is 0.8 square minus Q is 80 minus 80. Delta is 0.025, 5 square into U delta T is 0.2. So if you do the calculation correctly, this is going to come out as plus minus 0.018 watt per meter degree C. Okay, so this is the value of the uncertainty in the thermal conductivity. So you can say that your K is going to be what we found 0.4 watt per meters degree C. So that is 0.4 plus minus 0.018 watt per meter degree C. So this is the value of thermal conductivity. Okay.
Why is this in this example, in this question,
Yeah.
the direction of heat flow will be only axial, right? If I'm not wrong.
Which one?
The direction of heat flow
Yeah.
will be only axial.
This is the material thickness. Okay. The direction of heat flux will be through the thickness of the material. This is the material, right? This is the material. Since the ends are insulated, the heat cannot go in the lateral direction. This is the heater. So heat will only flow through this thickness. Okay. So this is a
Right.
rectangular geometry.
Okay.
And here heat loss is neglected. Okay. So the next question we will talk about where there is a heat loss that is considered.
Right.
So this is called the radial heat flow apparatus. Okay, this is the second method for measuring thermal conductivity. So a radial heat flow apparatus contains an oil sample, okay, SAE 40 lubricating oil in the annular gap of a radial flow thermal conductivity apparatus. So I will draw the radial flow thermal conductivity apparatus. The thickness of the oil layer is given. Heat transfer area has been estimated from the manufacturer data to be 0.0133 meters square. The electrical heater is specified to have a resistance of 53.5 ohm. The following data was collected in an experiment. Heater voltage is given, plug temperature is given, jacket temperature is given. What is the thermal conductivity of the oil sample? Okay, so first let us resolve that and then we'll calculate answer. So typically, as compared to a guided plate, which is rectangular in geometry, okay, because heat flow is happening either upward or downward. But in a radial heat flow apparatus, as the name suggests, heat flow direction is radial. Okay, so that means you have an axisymmetric scenario. So where you have a heated plug, okay. So this heated plug is surrounded by these radial heaters. So this is again axisymmetric. What we are seeing is a cross section, but it is axisymmetric. And you have then the sample, which is here. And the ends are insulated. Then you have some kind of flow scenario. So basically the gas or fluid whose temperature you want to measure, it gets in here, goes something like that in the circumferential direction and exits there. Okay, so this is the scenario. Here also, like the previous case, the heat transfer through the sample occurs only in the one dimension, because the ends are insulated and the temperature of the plug and heater are same, so the heat only leaves radially outward through the thickness of the sample. Okay, so the annular space is basically filled with the sample, that is the oil, whose thermal conductivity you want to measure, and the thickness of that oil layer is given. Okay, the heat transfer area, the heat transfer that takes place between the the heater and the sample, that is the oil layer, is given. The electrical heater has a resistance and voltage given. The temperature of the plug is given, and the jacket, which is the outer surface, is given. That is, both these basically indicate what is the temperature jump across the sample. Okay, one side of the sample has temperature of this, another side of the sample has temperature this. So what is the thermal conductivity of the sample, it is asking. Okay, now in this case we can also consider we have a correlation for a radial flow apparatus. The heat loss that can happen in a radial flow apparatus is related to the temperature jump. Okay, so this correlation I had given you in the class. So this is 0.0511 plus 0.206 into delta T plus 0.0118 delta T square minus 0.000153 delta T cube. So if you look through the slide, this relationship, which indicates the heat loss from the system, is specified as this. Okay, so this delta T is basically the temperature here minus the temperature there. Okay, so this is the jacket and this is the plug side temperature, which is the same as the heater temperature. So this temperature difference delta T is also given. Okay, so first let us find out how much heat that is supplied to the heater. So the heater is supplied with a voltage of 40 volt and it has a resistance of R of 53.5 ohm. So as you know, the heat supplied to the heater is given as I square R into T. Sorry, the rate of heat transfer will give you I square into R. This is the rate of heat transfer. That means per unit time, joule per second. So I square into R. So if you replace in terms of voltage, this will become V square divided by R. So your V is given 40 square. R is given, the resistance is given 53.5 ohm. So if we calculate how much heat is coming out of the heater, that is going to be 29.91 watt. So this much heat is coming from the heater. That means that this much heat is passing through the sample. Out of this Q dot, some heat is leaking out. Some heat loss is there. That heat loss can be calculated using this relation. Now this heat loss has a is dependent on delta T. So delta T is basically the temperature of the plug, which is same as the temperature of the heater, minus the temperature of the jacket. Okay, so temperature of the plug is 32.9 degrees centigrade and temperature of the jacket is 28.2 degrees centigrade. So the difference gives you 4.7 degrees C. So this, if we substitute in the QL expression, so the rate of heat loss can be found out as if you substitute 0.0511 plus 0.206 into 4.7 plus 0.0118 into 4.7 square minus 0.000153 into 4.7 cube. If you do the calculation, this will come out to be nearly 1.26 watt. So this much heat is getting lost, even if despite your effort to insulate, this much heat can go out. So your actual heat transfer through the element will be the Q from the heater minus what is getting lost. So that is 29.91 minus 1.26, that will be 28.95 watt. So now, similar to the previous case, we have an expression for thermal conductivity, and it is one-dimensional heat transfer. So that is basically Q into delta over delta T, right? So this is what the formula that we wrote here. Q delta over delta T, rate of heat transfer. So now this is the total heat transfer. So Q, you can write it as Q dot over A into delta over delta T. This is 28.95. The surface area through which heat transfer happens is calculated to be 0.0133. So that is given 0.0133 meters square into delta. The thickness of the sample is 0.3 mm. 0.0003 divided by delta T is 4.7 degrees centigrade. So if we calculate this correctly, we would get this as 0.138 watt per meter degree C. Okay. So this is the first part of the question.
Sir, I have a query over here. I'm sorry
Yeah,
to.
yeah.
Like K is equal to Q dot delta divided by delta T.
Yeah.
This expression, I'm sorry, sir, I could not gather it.
Here, this one.
Right, sir, exactly, sir, exactly.
So this we had derived, right, while solving the previous question.
Right, sir.
So we started with Fourier law of heat conduction. This is the Fourier law of heat conduction.
Okay.
We says that Q dot is minus K into dt by dx. Okay. So that means.
Okay, dt is divided by dt is considered as delta. Okay. Okay.
Yes. Okay. The dt by dx is basically the gradient, which is approximated as delta T over delta. Dx is like delta. Dt is like delta T. Okay.
So this is valid for even for radial thickness also, sir.
Yeah. So because the radial thickness, this delta, as long as delta is very small, this formula is valid. Okay.
Okay, sir.
Because a very small thickness, even in the radial coordinate system, can be considered as a one-dimensional problem. Okay. So that is why we are able to apply this.
Right.
The next part is that, so this part we answer. If the measured parameters are the following uncertainties, what will be the uncertainty, the estimated value of the, so the voltage has an uncertainty of 0.5 volt. The temperature has an uncertainty of 0.2 degrees centigrade. Okay. So, and it also says that our heat loss, the heat loss is having an uncertainty of 0.5%. Okay. So here, if we talk about this Q dot, right? Because thermal conductivity depends on this Q dot. So we have Q dot has uncertainty, and the uncertainty in Q dot is having the uncertainty from QH, and QH has uncertainty in V and temperature. Okay, so let me indicate the uncertainties. So this is having uncertainty. This is having uncertainty, which is coming from V and QL, right? So these three have uncertainties. Okay. How these uncertainties is affecting and are affecting the uncertainty in the K is something we need to know. So first we need to talk about how the uncertainties in the heat loss and B is affecting the Q. Okay, so let's first write. We have Q is basically Q from the heater minus Q heat loss. So from the heater, it is coming V square by R and minus the heat loss. So this has an uncertainty. This has an uncertainty. Okay. So U of V, the potential, uncertainty in the potential is plus minus 0.5 volt. So this is equal to plus minus 0.5 volt. And uncertainty in the QL, the heat loss, it is saying that it is 0.5%. So that means that is 0.5 divided by 100 into the heat loss, that is 1.26. Okay, so this is the uncertainty in the heat loss. First, let us find what is the uncertainty in the Q dot. So uncertainty in the Q dot will be, so first we also need to find the gradients. So del Q dot over del V will be 2V over R. Okay. And del Q dot over del QL dot will be simply -1, right? So this is going to be 2V over R into UV square plus -1 into UQL square root. So if we substitute the things here, the nominal voltage V is given as 40 volt. So 2 into 40. The resistance, nominal resistance is given as 53.5 ohm. So this is 53.5 ohm square plus minus 1 into UQL is 0.5 divided by 100 into 1.26 square, right? So that if I calculate correctly, this will give me plus minus 0.75 watt. Now, if I write down the expression, K is now Q over A into delta by delta T. So this has an uncertainty of UQ dot, and temperature has an uncertainty of, so this we just found out, plus minus 0.75. This is given. Q delta 2 is given, that is plus minus 0.2 degrees centigrade. So here we can find out the uncertainty in K. That is, first we need to find dou K over dou Q dot, that is delta by A delta T, dou K by dou delta T will be Q dot over A into minus 1 over delta T square. So we have delta by A delta T into UQ square plus Q dot by A delta T square into Q delta T square root. So we have all the values. Okay, we can just substitute. So delta happens to be the thickness, so that is 0.0003 divided by area of cross section is given as 0.0133. Delta T is given as 4.7 degree. Uncertainty in the Q is given as 0.75. Q dot is given as 28.95, and A is given as 0.0133. Delta T is 4.7 square into uncertainty temperature is 0.2. If I calculate this correctly, I will get this as plus minus 0.009. Okay, so my thermal conductivity K is going to be 0.138 plus minus 0.009 watt per meter degrees. Okay. So this is the radial heat flow apparatus. Okay, so maybe the last question for today. So this is a again the third method that we can use to measure thermal conductivity, and this is something we also discussed in the class. So here, typically we have a standard for a reference material. Then we have an unknown material whose thermal conductivity we want to measure, and the side walls are basically insulated. Let's say this is the temperature T1 at one end, at the other end temperature T2. This is material, let's say this is material A, this is material B. Let A be the standard material, the thermal conductivity is Ka, thermal conductivity is Kb. We measure temperature difference between these 2 points located at a distance of La in material A. Similarly, 2 points will be. So whatever, because of this temperature difference, whatever heat is going through the material A, same heat is going through material B because the ends are insulated. Okay. So this setup is called thermal conductivity comparator. This uses a standard reference material. Let's say this is the standard reference material. This thermal conductivity we are is 45 plus minus 2% watt per meter degree C. Two thermocouples placed 22 plus minus 0.2 mm apart indicates a temperature difference of 2.5 plus minus 0.2 degrees centigrade. So basically here delta TA is 2.5 plus minus 0.2 degrees centigrade. LA, the location difference between the thermocouples, is 22.25. The material of unknown thermal conductivity. So B is the material of unknown thermal conductivity. This is known, this is unknown. Unknown thermal conductivity is in series with the standard reference material and indicates a temperature difference of 7.3 plus minus 0.2 degrees C across a length of 20 plus minus 0.25 mm. Determine the thermal conductivity of the unknown sample, that is Kb, and its uncertainty. Okay, so how do we do? The principle is that whatever heat flux is going through material A, same heat flux is running through material B. That means Ka delta Ta over La. This is the heat flux going through material A. It will be same as heat flux going through material B, and that is again Kb into delta Tb over Lb. This is from Fourier law of heat conduction, right? Heat flux is K into temperature gradient. So basically Ka delta Ta over La will be Kb delta Tb over Lb, and we do not know Lb, Kb, so we find Kb as delta Ta over delta Tb Lb over La into K. So we can find out delta Ta over delta Tb is 2.5 divided by 7.3 Then LB over LA is 20 divided by 22. Then Ka is 35. So if you do the math, you can find Kb with 14 watt per meter degree C. Okay. Now we have to find the uncertainty in the thermal conductivity Kb that we just found. Okay. So the uncertainties are given in all four things: K, La, delta Ta. Sorry, 1, 2, 3, 4. You have delta TV also in LB. So basically, in this equation, all the uncertainties are given. Okay. So you can use the similar formula that we have used earlier. So you find del kV over each of these, delta Ta, del kV over delta PV, del kV over del LB. Okay. So evaluate each one of these, and for each you have the uncertainty. UKB is, for example, sorry, U delta TA, not KB is something that we want to determine. U delta TA is 0.2 degrees centigrade. Similarly, U delta TB is 0.2 degrees centigrade. ULB is 0.25 mm. So that is 10 to the power minus 3. Then LA is again 0.25. Then UK, thermal conductivity of A, that is 2%. 2 by 100 into 45. So you have all these gradients and you have all these uncertainties. So you just use that formula to find out uncertainty in the thermal conductivity of material B, which if you do the calculation correctly, it will come out to be something like plus minus 8.85%. It means that 8.85 divided by 100 into the thermal conductivity of B is 40. So it will be this much. Okay. So let me stop here. If you have any question, we can discuss.
Recording stopped.
Sir, sorry to interrupt.
Yeah.
Can you just explain the diagram that you have drawn for the last question alone?
So here, see, typically what happens is you have a standard material, okay, and whose thermal conductivity you already know, right? And you have another material which is given to you, a sample is given to you in the form of a rod, and you are asked to find the thermal conductivity of the rod. So what you do is the standard material and the sample you Both these you make in the form of this rod, which is your sample, and you place them on top of the standard material on top of the sample. Okay, they make metal to metal contact here. All around you basically insulate this perimeter here. You basically insulate. You can use cotton wool, for example, to insulate. Now, here you place some kind of heater that is at a temperature T1. Here you can use some kind of a heat sink or even ice or even ambient temperature at some T2. So the heat flow happen in this direction because this is hot end, this is cold end. You drill some holes into this material and insert thermocouple. Okay. Typically, you try to measure temperature at the center. Drill the hole to the center of this rod. Okay. And you measure temperature at two different points which are located at a distance of LA. And you measure this temperature difference to be delta T. Similarly, in material B, you measure temperature difference to be delta TB. And the difference between these 2 points, distance between these 2 points is LB. So then you use basically Fourier law of heat conduction to equate the heat fluxes. And from there, you can actually predict KV theoretically. And all these are known parameters now. These two are known from your experiment. These are geometrical parameters. Where did you drill your holes to put your thermocouples? This is already known. This is a standard material. So you can find KV. Okay.
Clear, sir. Thank you.
Okay, if there is no question, then we'll continue tomorrow.
Sure, sir. Thank you.
Thank you. Thank you very much, all of you.
Thank you, sir. Thank you so much.
Thank you, sir. Thank you, sir. Thank you very much.
Thank you very much, sir.
Thank you.